Welcome everybody. Today we have Holger from ADTRAN. He's working as a software development engineer at ADTRAN in Berlin. In the last year, his main focus was the broadband area, developing a G.fast products. As part of a cooperation between the ONF and ADTRAN for the A4 project from Deutsche Telekom, he's currently working at the implementation of an OpenONU adapter written in Golang. And this is going to be the topic of today's presentation. So without further ado, I'll give it the floor to Holger. And Holger, please go ahead.
Thank you, Andrea. Okay, welcome to the presentation of our project to implement an OpenONU adapter in Go language. This overview shows you the position of the OpenONU adapter within the VOLTHA framework. The main task of the OpenONU adapter is to interact with the real ONUs connected to the system. Especially, it has to terminate the OMCI stack towards the ONUs. Okay, what is the motivation behind our current project? The main requirement to the OpenONU adapter is that one instance has to serve at least 1024 ONUs. That means 32 ponds with 32 ONUs each. The existing Python OpenONU adapter showed scalability issues with this requirement. At the time being, 8 Python OpenONU adapter instances are necessary to support up to 1024 ONUs. This deployment of multiple Python ONU adapters leads to additional complexity of the system and increased consumption of processing power. That means one way out of this problem could be to replace the existing Python-based single-threaded OMCI library and OpenONU adapter by multi-threaded versions written in Go language. The goal is to make use of multi-threading features of the Golang to parallel communication with the particular ONUs. The existing functionality and capabilities of the Python version have to be kept. In the meanwhile, the porting of the OMC library was done already, whereas the porting of the OpenONU adapter is still in progress. To give you an impression on the current state of implementation, the following 2 slides list the features already implemented for the new Golang adapter. The Golang adapter comes up in VOLTHA Kubernetes framework. The BBSIM ONUs reach the state active and reason initial map downloaded. The OMCI data are received by the MIP upload process and stored in an internal database, not etcd yet. The ONU devices and ports are visible in ONUs. The adapter concurrency protection enhancements are deployed to ensure setup of multiple ONUs started in parallel. And the most important point here is that one adapter is able to bring up to 1024 BBSIM ONUs up to the state described above. Okay, second slide of already implemented features. And OMC MIP download to provide ONU basic config is implemented. The adapter is able to use existing MIP templates from the etcd to skip the MIP download process. And the configuration of device port admin state is supported. The adapter furthermore supports the processing of ONU upper status unreachable and down. And furthermore, we have a special robot test suite implemented to check the intermediate implementation steps and it is possible to support variable numbers of ONUs between 1 and 1024 with this test case. All the code is already merged to Git And if you are interested in the details of the implementation, you will find them in the Git repo listed above on this slide. Okay, as already mentioned, the main motivation to implement the Golang adapter was the lack of performance of the Python version. And therefore, the first runtime tests we made are looking very promising. The graph shows the time to reach the state initial MIP downloaded for the ONU for 65 ONUs, depending on the number of processing cores. This test scenario, the baby Sim environment was used with 8 ponds and 8 ONUs each. There was only one adapter instance installed, and we not used any MIP templates. That means the full MIP upload cycle was necessary for each of the ONUs. Here in this graph, you can see in blue color the Python version. And you see already for 2 cores, the Golang adapters much faster than the Python implementation. You can also see that the Python version does also benefit from the increased number of processing cores, but this comes to a flat line after, or you have already a basic number of seconds which will not be decreased anymore. For the Golang adapter, you see that for each increasement of cores, the time to bring up this 64 ONUs decreases also. Also not proportional, but there's some base time we could not go under. And you see for 24 cores, we have the Golang adapter processing 15 times faster than the Python version. There were also done some additional runtime tests. The following test results are available for the Go version only, since a single instance of the Python adapter ran into timeouts during the test for 512 and also literally for 1024 ONUs. It was the same test scenario as described before, and we used 24 cores, processing cores for this test. And you can see 512 ONUs reached this described state in about 80 seconds, and 1024 ONUs reached the state in 147 seconds roundabout. Okay, which features are currently open? We started to work on configuration of traffic profiles, tcont, the gem ports, and the traffic scheduler. And the change of port status according to physical events is open. Furthermore, we do not have full-blown error or timeout treatment. That means reporting and appropriate direction on it is not implemented. What is also missing is the ONU soft and hard reboot, and the OMCI alarm test performance and supervision and notification. There's no ONU software update currently implemented. The support of creation of MIP templates is open, and also the dynamic configuration of ports devices based on external config requests or on ONU state changes. It means we concentrated full on the straightforward approach currently. The supervision of response of to built-in liveliness and probe checks is not implemented, and also the complete storage of OMCA data within the etcd to enable automatic reflow. Okay, we are already at the end of the presentation. That's all I want to say.
Yes, thanks, Holger. That was a very good, clear and concise presentation. I think the results are very, very promising with what you have shown for us to go forward with the Go adapter in the future and really achieve a much better performance out of the system. So I kind of have two questions. The first one is more of a general one about the community and working in with the ONF stuff and VOLTHA in particular. So what challenges, what positive elements, negative elements you found while working in this new Kubernetes cloud native environment, and in particular with the VOLTHA deployment that you are contributing to?
Okay, I think the positivities are, for example, that the environment is easy to configure using the Helm charts. You have all the configurations centralized at one place, and it is it's a very good method to do this. Furthermore, I think the BVSIM is very good. It provides an excellent test environment near to the real behavior of the hardware. That means up to the current point, we only test with BVSIM and did not miss real hardware until now. And I think it is good to handle, and also the VOLTHA framework to bring up the VOLTHA script and so on. The only thing is working from home, when there's a change in the containers, then the download is lasts a really long time. But fortunately, I have super vectoring at home, so it works for me. Challenges, I think, in the first weeks or months, we were confronted with frequent changes in the external interfaces of VOLTHA libs. And sometimes the question arose if it is really worth the effort, the effect of these changes, the effort which is caused in all the other applications. But actually, that is a living project. I think we have to deal with this.
Yeah, no, I do agree. It is very true that the Helm configuration helps a lot, and BVSIM is incredibly valuable for our project. And yeah, I tend to agree with the fact that frequent changes to VOLTHA libgo do bring in some toil to the developers, but it's, again, as you said, it's the life of a master and a living project. And I think as the more and more we proceed, I think also you saw that the more and more we proceed, we have less and less changes to the protos, because those are kind of set in stone the more we go further with the project. So the second question is, you've seen tremendous benefits of using Go versus Python, and tremendous speed increases in achieving a certain state of the ONUs. So where do you think lies the most performance gains using the Golang versus the Python one?
I think the main benefit reached by using the Go routines to decouple the message processing of different ONUs. Furthermore, I think it's also a point that the Go is a compiled language and executes much faster than the interpreted Python code. So these two are points, I think, as you have seen in the runtime tests, even with 2 cores, the Go version is much faster because of the compiled code, which runs simply faster than the interpreted one. And in the higher numbers of cores, when you have more cores available, then the Go routines come into play to parallelize the bring up of the single ONUs. That's my impression. Mm-hmm.
Yeah, no, I tend to agree. That was the key bottleneck, was a single-threaded Python application, definitely. Mm-hmm. Okay, and what if somebody wants to join this this work that you guys are doing, that the community is doing? What are the next steps?
I think all open tasks are defined in ONF Jira. So if somebody wants to contribute, just grab one story. And what is probably also very important to join our bi-weekly meeting for the OpenONU adapter, to keep in touch regarding the progressing implementation. So
yeah,
if you want to contribute, just grab one.
yeah, and yeah, it's on Wednesday, I think, and it's on the public core calendar. So please, if anybody's interested, feel free to join that meeting. Last thing, you can see the code here, as Holger pointed out. Obviously, if you want to try it out, there is also the Docker container, which is up on Docker Hub. And you can easily change the minimal values file for kind VOLTHA and deploy it to that one, correct?
Yes.
Awesome. Perfect. Then that was all from my side and from my questions. So thanks a lot, Holger, for presenting, and thank you for contributing, you and your team. I would like to thank Michael too, and also Otger from Netsia for contributing. And thanks for the great work. I'll look forward to seeing more of the next steps implemented in the upcoming months.
You're welcome. Thank you.
Thanks a lot. Cheers.
Cheers.